There is a force in this universe that no one has ever seen, no one has ever touched, and no one fully understands. And right now, at this very moment, it is tearing space itself apart at a rate faster than light can travel. Not metaphorically, not approximately, literally. The fabric of the universe is expanding so rapidly at its outermost edges that the light from galaxies billions of light years away will never reach us. Those galaxies are not moving away from us through space. Space itself is stretching between us and them, carrying them beyond any conceivable reach, faster than the speed of light. And that is not a violation of physics. It is physics. It is the universe operating exactly as its own rules allow, in ways that took humanity nearly a century to even begin to comprehend. The force responsible for this has a name: dark energy. And despite accounting for roughly 68% of everything that exists in the universe, more than all the stars, all the planets, all the gas clouds, all the dark matter combined, scientists cannot tell you what it is. Not with confidence, not with consensus. The most precise instruments ever built by human civilization have measured its effects with extraordinary accuracy, and yet its fundamental nature remains one of the deepest unsolved mysteries in all of science. To understand why this matters, you need to hold a number in your mind. The observable universe, the portion of the cosmos that light has had enough time to reach us from since the Big Bang, spans approximately 93 billion light years in diameter. 1 light year is the distance light travels in a single year, moving at 300,000 kilometers per second. Traveling at that speed, crossing just our own galaxy, the Milky Way, would take roughly 100,000 years. The observable universe is nearly 1,000,000 times wider than that, and it is growing. Every second, in every direction, the boundary of what we can observe pushes outward, not because we are getting better at looking, but because space is physically expanding. Now here is where the story shifts from remarkable to deeply unsettling. For most of the 20th century, physicists and astronomers assumed that this expansion was slowing down. It had to be, by all reasonable logic. The Big Bang had set everything in motion roughly 13.8 billion years ago, and gravity, the most familiar force in nature, should have been pulling it all back together, decelerating the outward rush of galaxies the way Earth's gravity decelerates a ball thrown into the air. The universe was expected to be coasting, gradually losing speed, perhaps eventually reversing into what theorists once called the Big Crunch. The universe had other plans. In 1998, 2 independent teams of astronomers, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees at the High Z Supernova Search Team, made a discovery so contradictory to expectation that both teams spent months checking and rechecking their data, convinced they had made an error. They were measuring the brightness of a specific class of exploding stars called Type Ia supernovae. These stellar explosions are among the most powerful events in the known universe, briefly outshining entire galaxies containing hundreds of billions of stars. More importantly, they detonate with a remarkably consistent intrinsic brightness, consistent enough that astronomers can use them as what scientists call standard candles, meaning tools for measuring cosmic distances with precision. What both teams found was this: the supernovae were dimmer than they should have been, not slightly. Measurably, systematically, undeniably dimmer, which meant they were farther away than any slowing expansion could account for. The universe was not decelerating, it was accelerating. The expansion of space was speeding up, driven by something that was not gravity, not radiation, not any known particle or force. Something was pushing the universe apart, and it was winning. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The prize was well earned. They had not discovered a new planet or a new star. They had discovered that the dominant component of the entire universe was something no one had ever directly detected, a form of energy embedded in the fabric of space itself, invisible, uniform, and apparently inexhaustible. Dark energy. The name is more descriptor than definition. Dark, because it emits no light, reflects no light, interacts with no light. Energy, because its effects on the expansion of space are consistent with something that carries energy density, a value that appears to be constant throughout all of space, at all times, in every direction. In the equations of general relativity, Albert Einstein's framework for describing gravity and the structure of spacetime, dark energy corresponds to what Einstein himself once called the cosmological constant, a term he introduced in 1917 and later famously dismissed as his greatest blunder, only for the universe to vindicate it completely 8 decades later. Einstein originally added the cosmological constant to his field equations to prevent his model of the universe from collapsing under gravity. He wanted a static, eternal cosmos. When Edwin Hubble demonstrated in 1929 that the universe was expanding, that virtually every galaxy was receding from every other galaxy, its light stretched toward the red end of the spectrum by the very expansion of space, Einstein abandoned the constant. It was unnecessary for an expanding universe, he reasoned. He removed it. Then in 1998, reality reinserted it. That is worth sitting with for a moment. The greatest physicist of the modern era added a term to his equations, removed it in embarrassment, and 70 years later, observational evidence forced it back in. The universe, indifferent to human intuition, had simply been operating with a cosmological constant the entire time. There is a common misconception worth addressing directly. When people hear that the universe is expanding faster than light, the immediate response is often confusion or skepticism, because we were all taught that nothing can travel faster than light. That rule is real, and it holds. But it applies to objects moving through space. It does not apply to space itself expanding. There is no law of physics that limits how fast the metric of space, the measure of distance between 2 points, can grow. The galaxies at the observable edge of our cosmos are not violating relativity. They are sitting still in their local neighborhoods of space, just as we are sitting still in ours. The space between us is simply increasing at a rate that exceeds 300,000 kilometers per second. Those galaxies are not going anywhere. The distance between us and them is just growing relentlessly without limit. The analogy that comes closest to capturing this: imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots do not move across the surface. They stay fixed in place, yet the distance between every pair of dots increases simultaneously in all directions as the rubber stretches. Now imagine that the rubber is not just stretching, but stretching faster and faster with each passing second, driven by a pressure built into the rubber itself that no one can see or explain. That is the universe. That is dark energy. And what drives it, what actually causes the vacuum of empty space to carry energy, remains, as of today, one of the most profound open questions in all of physics. Quantum field theory, the framework that governs the behavior of subatomic particles with extraordinary precision, predicts that empty space should be filled with fluctuating quantum fields, and that these fluctuations should carry energy. When physicists calculate how much energy the quantum vacuum should contain and compare it to the measured value of the cosmological constant, the discrepancy is not small. It is not off by a factor of 2 or 10. It is off by a factor of 10 raised to the power of 120. That is a 1, followed by 120 zeros. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. Something is deeply, profoundly wrong with our understanding of either quantum mechanics or gravity or both, or perhaps with something we have not yet conceived of. The universe is accelerating into darkness, driven by a force we cannot name. 68% of everything that exists is something we cannot see, cannot measure directly, and cannot explain. And the expansion is not slowing down. Every billion years, the rate increases. Galaxies that are today merely unreachable will eventually be erased, not destroyed, but simply carried so far beyond the edge of what light can ever bridge that they will cease to exist, for any practical purpose, as part of any observable reality. The universe is not just large. It is becoming larger in a way that cannot be stopped, and may not even be survivable, for any civilization, anywhere, across any timescale long enough to matter. But here is what demands your full attention. The acceleration is not uniform in the models, and the latest data from the most sensitive telescopes ever built is beginning to suggest, quietly and with growing insistence, that dark energy may not be constant after all. The universe should have slowed down. Every calculation, every model, every intuition built from 4 centuries of observational astronomy pointed toward the same conclusion. Gravity, operating across cosmic scales, would gradually break the expansion set in motion by the Big Bang. The math was clean, the logic was sound, and it was wrong. What the supernova data revealed in 1998 was not a minor correction to an existing model. It was a structural collapse of the prevailing cosmological picture. The universe was not decelerating, it was accelerating, and had been for approximately 5 billion years, roughly the same age as our own solar system. For the first half of its existence, the universe did decelerate, just as gravity predicted. Matter was dense enough, and the cosmos compact enough, that gravitational attraction dominated. But at some point, as the universe expanded and matter thinned out, something else took over. Something that does not dilute as space expands. Something that grows more powerful in absolute terms as the volume of the universe increases. That last point carries weight that is easy to underestimate. Every other form of energy in the universe weakens as space expands. Radiation loses energy as its wavelengths stretch. Matter spreads thinner as volume increases. Dark energy does neither. Its energy density, the amount of energy per cubic meter of space, appears to remain constant even as the universe grows, which means that as space expands, the total amount of dark energy in existence increases. The bigger the universe gets, the more dark energy it contains, the faster it expands, the bigger it gets. This is not a cycle that stabilizes. It is a feedback loop with no known ceiling. To hold the scale of this in mind, if you took a single cubic meter of empty space, a box roughly the size of a large wardrobe, the dark energy contained in that volume is almost incomprehensibly small. Physicists estimate the energy density of dark energy at approximately 6 times 10 to the power of negative 10 joules per cubic meter. A single AA battery stores about 3,000 joules. That cubic meter of vacuum contains less dark energy than a single bacterium weighing down a scale. And yet, because the observable universe contains a volume of roughly 4 times 10 to the power of 80 cubic meters, the total dark energy budget of the cosmos is staggering. It outweighs everything else combined, all the hydrogen clouds, all the stellar remnants, all the black holes, all the dark matter, by a factor of more than 2 to 1. The question that consumed theoretical physicists through the late 1990s and into the 2000s was deceptively simple. Where does this energy come from? The most straightforward answer, and in physics, straightforward answers deserve the deepest scrutiny, is the cosmological constant. In general relativity, Einstein's field equations allow for a term that assigns an intrinsic energy density to the vacuum of space. Not to any particle in space, not to any field excited above its ground state. To the vacuum itself, in its most empty, lowest energy condition. This term, represented in the equations by the Greek letter lambda, acts as a kind of pressure built into the geometry of space-time, a repulsive effect that counteracts gravity on the largest scales. When Perlmutter, Rees, and Schmidt published their results, the cosmological constant was immediately rehabilitated as the leading candidate. It fit the data. It required no new exotic physics beyond what Einstein had already written. The universe simply had a non-zero vacuum energy, and that energy drove accelerated expansion. The model that incorporated this, combining ordinary matter, dark matter, and a cosmological constant, became known as lambda CDM, with lambda representing dark energy and CDM standing for cold, dark matter. It is today the standard model of cosmology, supported by an extraordinary convergence of independent measurements from supernovae, the cosmic microwave background, and the large-scale structure of galaxy clusters. The problem is that lambda CDM tells us what dark energy does with remarkable precision. It says almost nothing about what dark energy is. Quantum field theory, the framework that underlies all of particle physics and has been tested to greater precision than any other theory in the history of science, makes a very specific prediction about vacuum energy. According to quantum mechanics, empty space is not truly empty. The uncertainty principle, one of the foundational results of quantum theory, states that the energy of any region of space cannot be precisely zero. Instead, the vacuum seethes with quantum fluctuations, pairs of virtual particles constantly blinking in and out of existence, borrowing energy from the vacuum and repaying it on timescales too short to directly observe. These fluctuations are not hypothetical. Their effects have been measured directly in multiple experiments, most famously in the Casimir effect, where two uncharged metal plates placed extremely close together in a vacuum are measurably pushed toward each other by the asymmetry and vacuum fluctuations on either side of them. Virtual particles are real. Vacuum energy is real. And when physicists use quantum field theory to calculate the total energy density of the vacuum, summing the contributions from all known quantum fields, the result is a number, a very large number. Depending on where the calculation cuts off, the predicted vacuum energy density comes out somewhere between 10 to the power of 60 and 10 to the power of 120 times larger than the measured value of the cosmological constant. 10 to the power of 120, written out, that is a 1 followed by 120 zeros. The ratio of the theoretically predicted vacuum energy to the observed dark energy density is a number so large it has no meaningful analog in human experience. The entire observable universe contains roughly 10 to the power of 80 protons. The number of Planck volumes, the smallest meaningful unit of space, in the observable universe is approximately 10 to the power of 185. The discrepancy between quantum field theory's prediction and the measured cosmological constant dwarfs both. It is, by universal agreement among physicists, the worst prediction in the history of science. This is called the cosmological constant problem, and it has no accepted solution. Two responses to this problem have dominated theoretical physics for decades. The first is that quantum field theory is somehow overcounting. Perhaps the contributions from different quantum fields cancel each other out through some unknown symmetry, leaving a remainder so small it matches the observed value. Supersymmetry, a theoretical framework that pairs every known particle with a heavier partner, was once the leading candidate to provide exactly this kind of cancellation. Supersymmetry predicted that the contributions from fermions and bosons to vacuum energy would cancel almost perfectly, leaving a residual that could match the cosmological constant. The Large Hadron Collider at CERN was expected to find evidence of supersymmetric particles in the early 2000s and 10s. It found none. As of the mid-2000s, supersymmetry remains theoretically viable but experimentally unconfirmed, and the cancellation mechanism it promised has not materialized. The second response is more philosophically radical and more uncomfortable. Perhaps the cosmological constant has the value it has not because of any deep physical principle, but because we happen to live in a region of a vastly larger multiverse where the constant takes this particular value. In most regions of this multiverse, the cosmological constant is either so large that matter never clumps into galaxies and stars, or so negative that the universe collapses long before any complexity can arise. Only in regions where it falls within a narrow window, close to what we observe, can galaxies form, stars ignite, planets coalesce, and observers exist to measure it. This is called the anthropic argument, and while it is logically coherent, it is scientifically unsatisfying. It explains the observed value not through dynamics or symmetry, but through selection. Critics argue it is unfalsifiable, and therefore not physics in any testable sense. Neither answer has closed the case. What has emerged in the years since the initial discovery is an increasingly precise portrait of dark energy's behavior over cosmic time. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the temperature fluctuations in the cosmic microwave background, the faint thermal afterglow of the Big Bang itself, with enough precision to independently confirm that the universe is geometrically flat and that dark energy accounts for approximately 68.3% of its total energy content. The Planck satellite, operated by the European Space Agency from 2009 to 2013, sharpened those measurements further, producing the most detailed map of the early universe ever constructed and reinforcing the Lambda CDM model with extraordinary statistical confidence. And yet, Threading through the data from Planck, from the Dark Energy Survey, and from successive generations of supernova catalogs, a subtle tension began to appear. A tension that did not resolve as the measurements improved. A tension that, if anything, deepened. The Hubble constant, the number that describes the current rate of expansion of the universe, can be measured two ways. One method uses the cosmic microwave background and the physics of the early universe to predict what the expansion rate should be today. The other uses local measurements, supernovae, Cepheid variable stars, gravitational lenses, to directly measure how fast nearby galaxies are receding. The two methods should agree. They do not. The discrepancy between them, now measured at a statistical significance exceeding 5 sigma, the threshold physicists typically require before declaring a discovery, has been named the Hubble tension, and it is currently one of the most actively debated problems in cosmology. 5 sigma means the probability of the discrepancy arising from random measurement error alone is less than 1 in 3.5 million. The two measurements are not converging. They are holding firm at their disagreement, and the instruments making them keep getting more precise. Something is missing from the model, something that affects how the universe has expanded at different epochs in its history. Something that the cosmological constant, in its elegant simplicity, does not account for. The data from the Dark Energy Spectroscopic Instrument, DESI, released in 2024 and followed by updated results through 2025, pushed this further. Mapping the three-dimensional positions of tens of millions of galaxies across cosmic time, DC found statistical hints that the dark energy density may not be constant, that it may have varied over the history of the universe, that lambda may be an approximation, a first-order description of something richer, more dynamic, and far stranger. If dark energy evolves over time, it is not the cosmological constant. It is something else entirely. The name physicists use for this possibility is quintessence, a dynamical scalar field permeating all of space, rolling slowly along its potential energy curve, driving acceleration now, but perhaps weakening in the future, or strengthening. Unlike the cosmological constant, quintessence would have changed throughout cosmic history, leaving imprints in the large-scale structure of the universe that precise enough surveys might detect. The DESI data are not yet definitive. The statistical significance of the deviation from a constant lambda sits at roughly 2 to 3 sigma, suggestive but not confirmed. But the direction of the hint is consistent across multiple independent analyses. The universe may be telling us that its dominant component is not static, not a fixed property of spacetime, but a living field, evolving on timescales of billions of years, with a future behavior that no current theory can confidently predict. And if quintessence is real, if dark energy is a field rather than a constant, then the question of where it is going becomes urgent in a way that the cosmological constant never was. A constant lambda accelerates expansion forever at a steady rate. A dynamic field could do something far more extreme. It could strengthen without limit. It could drive the expansion not just to acceleration, but to a divergence so violent that space itself tears apart on scales smaller and smaller, shredding first galaxy clusters, then galaxies, then solar systems, then planets, then atoms, in a sequence cosmologists have named the Big Rip. The equations that permit this scenario are not exotic. They follow directly from general relativity, with a single parameter, the dark energy equation of state, pushed past a specific threshold. And the current data do not rule it out. The measurements that could settle this question one way or another are already being gathered. The Euclid Space Telescope, launched by the European Space Agency in 2023 and returning science data through 2025 and beyond, is conducting the most ambitious survey of cosmic structure ever attempted, mapping the shapes and positions of billions of galaxies across 10 billion light-years of cosmic history, using the subtle distortions of gravitational lensing and the acoustic imprint of the early universe to trace how dark energy has behaved across time. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will extend this program further still. The answer is coming. But the question it may force us to confront, what dark energy actually is, at the level of fundamental physics, remains entirely open. And the deeper physicists look, the more they find that the answer will not come from tweaking what we already know. It will require something new. General relativity is not an intuition. It is a geometry. When Albert Einstein published his field equations in November of 1915, he did not describe gravity as a force pulling objects together, the way Newton had framed it 2.5 centuries earlier. He described gravity as the curvature of space-time itself, caused by the presence of mass and energy. Matter tells space-time how to curve. Curved space-time tells matter how to move. The two are inseparable, locked in a continuous geometric dialogue that governs everything from the orbit of Mercury to the bending of light around the sun to the expansion of the entire universe. The universe, in general relativity, is not a container with galaxies inside it. It is a four-dimensional manifold, a continuous fabric of 3 spatial dimensions and 1 time dimension, whose geometry is dynamically shaped by everything it contains. When cosmologists talk about the expansion of the universe, they are not describing galaxies flying outward through a pre-existing empty space. They are describing the metric of space-time itself changing, the mathematical measure of distance between every pair of points in the universe increasing over time, uniformly, in every direction simultaneously. This is encoded in a single equation called the Friedmann equation, derived in 1922 by the Russian mathematician and physicist Alexander Friedmann, directly from Einstein's field equations. The Friedmann equation describes how the expansion rate of the universe, represented by the Hubble parameter, changes over time as a function of what the universe contains. Matter slows expansion. Radiation slows expansion. But a positive cosmological constant, a vacuum energy density, drives acceleration. The equation is not ambiguous. It does not require exotic assumptions. It is a clean, mathematically rigorous consequence of general relativity applied to a homogeneous, isotropic universe. The Friedmann equation can be written in a form that reveals the competition between these components with stark clarity. On one side sits the square of the Hubble parameter, the expansion rate. On the other, a sum of terms. One proportional to matter density, one to radiation density, one to the curvature of space, and one to the cosmological constant. As the universe expands, matter density falls as the cube of the scale factor, the number describing how much the universe has stretched relative to some reference size. Radiation density falls even faster, as the 4th power. But the cosmological constant term does not fall at all. It remains fixed. And so as the universe grows, the other terms shrink toward irrelevance, and lambda, dark energy, comes to dominate. This is not a future scenario. It has already happened. We are living inside it. The universe today is approximately 68% dark energy, 27% dark matter, and roughly 5% ordinary baryonic matter. The atoms that make up stars, planets, gas clouds, and every human being who has ever lived. That 5% is everything visible, everything detectable by conventional telescopes, everything that has ever been directly observed in the history of astronomy. It is a rounding error in the cosmic ledger. The universe we can see and touch and measure is a thin residue floating on top of 2 components that interact with light not at all. Dark matter, at least, has gravitational effects that are directly measurable. It clusters. It forms halos around galaxies. It seeds the cosmic web of filaments and voids. Its existence was inferred by Fritz Zwicky in 1933 from the anomalous velocities of galaxies in the Coma cluster, and confirmed independently through the rotation curves of spiral galaxies measured by Vera Rubin and Kent Ford in the 1970s. The outer regions of spiral galaxies rotate far too fast to be explained by the visible mass alone. The stars and gas we can see cannot provide enough gravitational pull to hold them in orbit. Something invisible, massive, and distributed in extended halos around galaxies must be providing the additional gravity. Dark matter does not emit, absorb, or reflect electromagnetic radiation at any wavelength. But its gravitational fingerprint is everywhere, and no alternative theory of gravity has successfully reproduced all of its observed effects without invoking some form of additional non-luminous mass. Dark energy is a different problem entirely. It does not cluster. It does not form halos or filaments. It is perfectly uniform throughout space, contributing no gravitational attraction between objects, only a large-scale repulsive pressure that acts on the geometry of spacetime as a whole. And unlike dark matter, whose effects appear at the scale of individual galaxies and clusters, dark energy is invisible at those scales. Gravity still governs the local universe. The Milky Way is not being torn apart by dark energy. The solar system is not expanding. Even the local group, the collection of galaxies gravitationally bound to the Milky Way, including the Andromeda Galaxy and dozens of smaller companions, is held together by gravity, immune to the cosmic acceleration that is driving everything beyond it away. The threshold is distance. Gravity falls off with the square of distance between objects. Dark energy's effect is proportional to the distance itself. It does not weaken at greater separations. At small scales, gravity wins absolutely. At scales of tens of millions of light years and beyond, dark energy begins to win. The boundary between these regimes, the scale at which dark energy's repulsion balances gravitational attraction, lies at roughly a few megaparsecs, where 1 megaparsec equals approximately 3.26 million light years. Everything gravitationally bound within that threshold stays bound. Everything beyond it is being carried away, accelerating with every passing billion years. To translate this into human terms, if the Milky Way were the size of a dinner plate, the Andromeda Galaxy would sit roughly 3 feet away, close enough at that scale that their mutual gravity will eventually draw them together in a merger expected in about 4.5 billion years. The nearest galaxy cluster outside our local gravitationally bound neighborhood, the Virgo cluster, would sit at roughly the distance from New York to Los Angeles. And it is already accelerating away from us right now at a speed that will only increase. On the scale of the full observable universe, scaled to the dinner plate Milky Way, the most distant galaxies we can currently detect would sit tens of miles away, and the distance to all of them is growing, second by second, driven by dark energy. The equation of state of dark energy, the ratio of its pressure to its energy density, denoted by the letter W, is one of the most closely watched numbers in modern cosmology. For the cosmological constant, W equals exactly -1. This is not arbitrary. It follows directly from the thermodynamics of a vacuum energy. A fluid with negative pressure equal in magnitude to its energy density expands without doing work on its surroundings, maintaining constant energy density as the universe grows. If W equals -1 precisely, dark energy is the cosmological constant. It will drive expansion forever at an ever-increasing rate, but without any divergence. The universe will expand exponentially into an endless cold darkness, but it will do so smoothly. Gravitationally bound structures, galaxies, clusters, solar systems, will survive indefinitely, isolated from each other by the growing void between them. If W is less than -1, a regime physicists call phantom energy, the situation is categorically different. Phantom energy has a pressure more negative than its energy density. Its effective repulsion grows stronger over time as the universe expands. In this regime, the expansion rate does not merely accelerate, it diverges in finite time. The repulsive force eventually overwhelms gravity at progressively smaller scales, first tearing apart galaxy clusters, then individual galaxies, then solar systems, then planetary surfaces, then molecules, then atoms, then atomic nuclei themselves, in a final cataclysm that rips apart the very fabric of matter at every scale simultaneously. This is the Big Rip. It was formally described by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in a 2003 paper in Physical Review Letters. Their calculations showed that if W equals -1.5, the Big Rip would occur approximately 22 billion years from now. If W equals -1.1, it is pushed further into the future, hundreds of billions of years away. The exact timing depends entirely on the value of W, which observations are still working to pin down. The current best measurements from Planck, combined with supernova and baryon acoustic oscillation data, constrain W to a value consistent with -1, but with uncertainties that do not yet rule out phantom energy. The error bars overlap -1 on both sides. The DESI results from 2024 suggested a mild statistical preference for W evolving over time. for a value above -1 in the early universe and potentially below -1 today. This is called the phantom crossing, and it is one of the most theoretically challenging scenarios possible, because most physically consistent dark energy models cannot cross the phantom divide without introducing instabilities into the equations. The physics of why this is difficult requires a brief excursion into field theory. The simplest dynamical dark energy model, quintessence, describes dark energy as a scalar field slowly rolling down a potential energy curve. As the field rolls, its equation of state evolves, but it stays above -1. To reach phantom behavior, a different kind of field is required, one with a kinetic energy term of the wrong sign called a phantom field. Phantom fields are problematic because they can lead to an unbounded growth in quantum fluctuations, potentially destabilizing the vacuum itself. Some theorists have proposed hybrid models, called quintom models, that use both a quintessence field and a phantom field, allowing the combined system to cross the phantom divide while remaining mathematically stable. But quintom models require two independent scalar fields whose properties and interactions are entirely unconstrained by current theory. None of these theoretical constructs have been experimentally confirmed. They are frameworks, mathematically consistent possibilities that the data have not yet eliminated. The universe does not care which one physicists find most elegant. What makes this period in cosmology genuinely extraordinary is the convergence of high-precision surveys that are simultaneously constraining dark energy from multiple independent directions. Baryon acoustic oscillations, the frozen imprint of sound waves that propagated through the hot plasma of the early universe before recombination, leave a characteristic scale in the distribution of galaxies across the sky. That scale, roughly 500 million light-years today, acts as a standard ruler. By measuring how large it appears at different distances, astronomers can reconstruct the expansion history of the universe across billions of years of cosmic time with extraordinary precision. DESI's galaxy survey has mapped this ruler across a range of redshifts deeper and broader than any previous instrument, producing a timeline of cosmic expansion that spans roughly the last 11 billion years. Weak gravitational lensing, the subtle distortion of background galaxy shapes by foreground mass concentrations, provides an independent window into how cosmic structure has grown over time, and therefore how dark energy has suppressed or enhanced that growth. The Euclid mission is conducting weak lensing measurements across 1 billion galaxies, with a statistical precision that will reduce the uncertainty on W to below 1%. 1%. That is the margin within which the nature of the universe's fate will be determined. The data are not yet there. The answer is not yet known. But the instruments are running, the photons are being collected, and every night that passes adds another layer of precision to the most consequential measurement in the history of cosmology. The number that will tell us whether the universe ends in cold silence or violent dissolution is being measured right now, in observatories on high desert plateaus and in satellites drifting in the quiet dark beyond Earth's atmosphere. And the early results are not behaving the way the simplest theory predicted. In the spring of 2024, the scientific community received a result that had been quietly anticipated for years, and still managed to land with the weight of genuine surprise. The Dark Energy Spectroscopic Instrument, mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, released its first-year data analysis. DESI had spent 12 months scanning the sky with 5,000 robotic optical fibers, each one precisely repositioned every 20 minutes to lock onto a new target galaxy or quasar, measuring the redshift of their light with spectroscopic precision. In that single year, it had collected spectra for more than 6 million galaxies and quasars, more than all previous spectroscopic surveys in history combined. It had mapped the three-dimensional distribution of matter across the universe from the present day back to roughly 11 billion years ago, when the universe was less than a quarter of its current age. The result that emerged from that dataset was not a confirmation. It was a deviation. When the DESI team fitted their baryon acoustic oscillation measurements to cosmological models, the data showed a statistically significant preference, at roughly 3.9 sigma across their full dataset, for a dark energy equation of state that was not constant, not W equals -1, not the cosmological constant, Instead, the data preferred a model in which W had been closer to -1, or even above it, in the early universe, and had evolved to a value below -1 today. The dark energy that appears to dominate the universe right now behaves differently than the dark energy that was present 5 or 8 billion years ago. 3.9 sigma is not a discovery by the strict 5 sigma standard of particle physics, but it is not noise. It survived multiple independent cross-checks within the DESI team. It was consistent across different subsamples of the data: luminous red galaxies, emission line galaxies, quasars, all pointing in the same direction. And when the DESI results were combined with external datasets, the Planck cosmic microwave background measurements, the Pantheon Plus Type Ia supernova compilation, and weak lensing surveys, the statistical preference for evolving dark energy strengthened further. The cosmological community reacted with the specific kind of cautious intensity that characterizes genuine scientific uncertainty at its most productive. Not dismissal, not proclamation. Rigorous, methodical pressure testing of every assumption in the analysis pipeline. What made the DESI result particularly striking was not just its statistical weight, but its theoretical implications. If dark energy evolves and if W changes over cosmic time, then the cosmological constant is ruled out as the complete explanation. Lambda, by definition, does not evolve. A constant is a constant. An evolving equation of state demands a dynamical component, a field that changes, that has a history, that will have a future different from its present. The universe's dominant energy component would need to be understood not as a fixed geometric property of space-time, but as a physical degree of freedom, something that can, in principle, be described by its own equations of motion, its own potential energy landscape, its own interactions. The theoretical frameworks already existed, waiting on the shelf. Quintessence models, scalar fields with slowly evolving equations of state, had been developed through the late 1990s and 2000s precisely in anticipation of data that might deviate from lambda. The simplest quintessence models, called thawing models, have a scalar field that starts nearly frozen, pinned near the top of its potential by the Hubble friction of the rapidly expanding early universe, and only recently began rolling, causing W to depart from -1 toward less negative values. Freezing models reverse this. The field was rolling in the early universe and is slowing down, with W approaching -1 from above. Neither of these standard quintessence classes naturally produces a W that crosses below -1. The DESI preference for W below -1 today is precisely what places it in theoretically difficult territory. A field with W less than -1, phantom behavior, violates what is called the null energy condition, a foundational assumption in classical general relativity that states that the energy density measured by any physical observer must be non-negative. Phantom fields formally violate this condition, and in doing so, they open theoretical doors that most physicists would prefer to keep closed. Instabilities in the quantum vacuum, unbounded growth of perturbations, and the eventual divergence of the scale factor in finite time. There is, however, a way to produce apparent phantom behavior without a true phantom field. Modified gravity theories, frameworks that alter the behavior of general relativity at cosmic scales, can mimic a dark energy equation of state below -1 without introducing any scalar field at all. In these models, it is not that a new energy component is pushing space apart with a pressure more negative than its energy density. It is that gravity itself behaves differently on large scales than Einstein's equations predict, that the curvature of space-time responds to matter and energy in a modified way that produces additional acceleration. The most widely studied example is FR gravity, in which the standard Einstein-Hilbert action, the mathematical object from which general relativity's equations are derived, is replaced by a more general function of the Ricci scalar, the quantity that measures the local curvature of space-time. Different choices of this function produce different modifications to the expansion history and to the growth of cosmic structure. Modified gravity theories make predictions that differ from dark energy models, not just in the expansion rate of the universe, but in how fast structure grows. In standard lambda CDM, the rate at which galaxies cluster together over cosmic time follows a specific pattern determined by the competition between gravitational attraction and the suppression caused by dark energy. Modified gravity theories generally predict a different growth rate, sometimes faster, sometimes slower, which leaves a distinct imprint in weak lensing measurements and in the clustering statistics of galaxy surveys. This is the lever that current and upcoming surveys are using to distinguish between dark energy and modified gravity as the source of cosmic acceleration. The tension between these two classes of explanation is not merely academic. It maps directly onto one of the deepest unresolved questions in fundamental physics, whether gravity, as described by general relativity, is the correct theory of space-time geometry on all scales. General relativity has passed every experimental test conducted within the solar system and in the strong field regime of merging neutron stars and black holes with extraordinary precision. But cosmological scales are different. The curvature of space-time caused by a neutron star merger is enormous. The curvature relevant to the cosmic expansion is almost imperceptibly small, and it is precisely in this regime, where gravity is weakest and acts over the largest distances, that deviations from general relativity might first become detectable. 1998 was the year the universe's acceleration was discovered. 2024 may come to be remembered as the year the first credible crack appeared in the simplest explanation for that acceleration. The follow-up was immediate. The DESI collaboration began processing its second and third-year datasets, with dramatically increased galaxy counts that will reduce statistical uncertainties by roughly 40%. The Rubin Observatory Legacy Survey of Space and Time, LSST, began its 10-year imaging survey of the southern sky in early 2025 from its site on Cerro Pachón in Chile, equipped with a 3.2 gigapixel camera, the largest digital camera ever built for astronomical use, capable of imaging an area of sky 40 times the size of the full moon in a single exposure. Over 10 years, it will photograph the entire accessible southern sky approximately 800 times, building a time domain record of billions of galaxies, millions of supernovae, and the subtle, weak lensing signal of dark matter and dark energy across the full history of cosmic structure formation. The Nancy Grace Roman Space Telescope, NASA's next flagship observatory, will complement Rubin's ground-based survey with a space-based wide-field infrared view, reaching deeper redshifts and measuring galaxy shapes with a precision impossible from within Earth's atmosphere. Its coronagraph instrument will also probe planetary systems, but its primary cosmological mission is a wide-field survey designed specifically to constrain dark energy and measure the Hubble constant with sub-percent precision. Together, these instruments represent a qualitative leap in humanity's ability to read the expansion history of the universe. The measurement precision they will achieve over the next decade is sufficient to detect a deviation from W equals -1 at the level of a few percent, small enough to definitively confirm or rule out the DESI hint, and to discriminate between competing dark energy models at a level of statistical confidence that leaves no room for ambiguity. But the DESI result is not the only anomaly threading through the current cosmological data. A separate and independently troubling signal emerged from a detailed reanalysis of Planck cosmic microwave background data combined with galaxy lensing measurements. A quantity called S8, which encodes the amplitude of matter clustering in the universe, measured at late times from weak lensing surveys, is consistently lower than the value predicted by the early universe Planck data under the assumption of lambda CDM. This is the S8 tension, and it has persisted across multiple independent weak lensing surveys. The Kilo Degree Survey, the Dark Energy Survey, and the Hypersuprime CAM Survey, all finding less clustering of matter in the late universe than the standard model predicts. One tension could be a systematic error. Two independent tensions pointing in the same direction, toward a universe that is expanding faster than predicted and clustering less than predicted, begin to outline the shape of something real, something that the standard model is missing. The possibilities are constrained but not narrow. Dark energy that strengthens over time could simultaneously drive faster expansion and suppress the growth of structure by accelerating the expansion before matter has time to fully collapse into clusters. Modified gravity that weakens on large scales could reduce the growth rate of structure while leaving the background expansion nearly unchanged. A coupling between dark energy and dark matter, a possibility called interacting dark energy, could transfer energy between the two components in a way that affects both the expansion history and the clustering amplitude simultaneously. None of these possibilities have been confirmed. All of them are consistent with the current data within its uncertainties. What is no longer consistent with the full body of current data, taken together, is the comfortable certainty that the simplest model, a cosmological constant in an otherwise standard universe, is a complete description of reality. The cracks are small, they are precise, and they are not going away as the measurements improve. In the history of physics, this is exactly how paradigm shifts begin. Not with a single dramatic refutation, but with a growing collection of precise measurements that the existing framework cannot simultaneously accommodate, each one small enough to dismiss individually, but collectively forming a pattern that demands a new explanation. The universe accelerated. That much is established beyond any reasonable scientific doubt. Why it accelerates and whether the force driving that acceleration is changing, those questions are now being answered in real time by instruments of unprecedented precision pointed at the oldest light in the universe. And the data, quietly and insistently, are beginning to say that the answer is not what anyone expected. There is a moment in the future of every galaxy now beyond our gravitational reach when its light traveling toward us at 300,000 kilometers per second will simply stop arriving. Not because the galaxy has died, not because anything catastrophic has happened to it, but because the space between us and it will be expanding faster than the light can cross it. The photons will still be traveling. They will never stop traveling. They will spend eternity crossing a distance that is growing faster than they can traverse it, and they will never arrive. From that moment forward, that galaxy, with all its hundreds of billions of stars, its own planetary systems, its own history of stellar birth and death spanning billions of years, will be causally severed from us, gone, not destroyed, unreachable, forever. This is already happening. Right now, the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, contains roughly 2 trillion galaxies. But the number of galaxies we will ever be able to observe, integrated across all of future time, is far smaller. Galaxies beyond a certain distance are already receding faster than light. Their most recently emitted photons are traveling toward us and making progress. The expansion is not yet fast enough to trap them permanently, but that window is closing. Cosmologists calculate that the total number of galaxies that will ever be observable from Earth, no matter how long humanity or any successor civilization waits, is approximately 100 billion. The remaining 1.9 trillion are already, functionally, gone. This is the first consequence of dark energy that operates on a timescale relevant to the future of intelligence in the universe. It is not a violent end. It is a slow, silent quarantine. Each gravitationally bound island of matter progressively isolated from every other, surrounded by an ever-deepening void that no signal, no probe, no photon will ever successfully cross. The timescales involved demand a different kind of numerical intuition. The current age of the universe is approximately 13.8 billion years. The sun will exhaust its hydrogen fuel and expand into a red giant in roughly 5 billion years, a future so distant that the continents of Earth will have rearranged themselves dozens of times before it occurs. On cosmological timescales, that is recent. The era of star formation in the universe, the period during which gas clouds are collapsing into new stars at a significant rate, will persist for perhaps another 100 trillion years, though the rate has already been declining since it peaked approximately 10 billion years ago. After the last stars burn out, the universe will enter a sequence of increasingly dark and cold epochs. The degenerate era, when only white dwarfs, neutron stars, and black holes remain. The black hole era, when even those stellar remnants have decayed or been consumed. And finally, the dark era, a state of maximum entropy from which no thermodynamic work can be extracted and no information can be meaningfully processed. Against this backdrop, the question of what dark energy does over cosmological time becomes the question of what the universe's ultimate fate actually is. In the scenario where W equals exactly -1, the pure cosmological constant, the expansion continues forever, accelerating exponentially, driving all unbound structures beyond the cosmic horizon. The Milky Way and Andromeda, which will have long since merged into a single massive elliptical galaxy, sometimes called Milkomeda by cosmologists, will persist as a gravitationally bound island, along with the other members of the local group. But beyond the local group, every other galaxy cluster, every other supercluster, every other structure in the observable universe will eventually redshift beyond detection and beyond causal contact. In roughly 150 billion years, the night sky, from any planet still orbiting a star in Milkomeda, will be completely dark. Not because stars have died, but because every other galaxy will have crossed the cosmic horizon and vanished. The universe, to any observer within that future galaxy, will appear to contain only themselves. The evidence for this future is not speculative. It is the direct extrapolation of measurements already made, constrained by data from the Planck satellite, the Pantheon supernova compilation, and the Baryon acoustic oscillation maps. If the cosmological constant is truly constant, this is what happens. The math is unambiguous. But the Deci results and the Hubble tension and the S8 tension together raise a different possibility, one whose endpoint is not cold isolation, but active destruction. If dark energy is a dynamical field, if W is evolving and currently trending toward values below -1, then the future of the universe depends entirely on whether that evolution continues, reverses, or diverges. A phantom field with W persistently below -1 generates a repulsive pressure that grows stronger as the universe expands. The scale factor, the mathematical quantity describing how stretched the universe is, does not just increase exponentially in this scenario. It diverges. It reaches infinity in a finite amount of time. Robert Caldwell's 2003 calculation gave the first quantitative picture of what this divergence looks like from the inside. Approximately 200 million years before the Big Rip, an interval shorter than the time that has passed since the Permian-Triassic extinction on Earth, the Milky Way and all other gravitationally bound galaxy clusters will begin to be pulled apart by the expanding dark energy. The repulsive pressure will have grown strong enough to overcome the gravitational binding energy of structures that have persisted for billions of years. 60 million years before the end, roughly the time since the Chicxulub impactor ended the Cretaceous, our own galaxy will be torn apart. Individual star systems will be flung from their positions in the galactic disk as the space between them expands faster than gravity can compensate. 3 months before the final divergence, the solar system itself will come apart. The planets will spiral outward from the sun as the expansion overwhelms the gravitational bonds holding them in orbit. 30 minutes before the end, the Earth will be torn from its own surface gravity. In the final fraction of a second, matter at every scale, continents, rocks, molecules, individual atoms, and ultimately atomic nuclei themselves, will be ripped apart by the diverging expansion. The strong nuclear force, which binds protons and neutrons together with a binding energy of roughly 8 million electron volts per nucleon, will be overcome by the repulsive pressure of phantom dark energy at scales of 10 to the power of -15 meters, the scale of atomic nuclei. At that moment, the fundamental structure of matter will dissolve. This is not fiction. It is the direct mathematical output of general relativity applied to a universe with a phantom dark energy equation of state, carried to its logical conclusion. Whether the universe actually takes this path depends on a number, W, that current observations have not yet pinned down precisely enough to confirm or exclude this scenario. What the observations have established is the scale of the acceleration already underway. The universe today is expanding at a rate described by a Hubble constant of approximately 67 to 73 kilometers per second per megaparsec, the range reflecting the Hubble tension between early and late universe measurements. At the lower end of that range, a galaxy 1 megaparsec away, roughly 3.26 million light-years, is receding from us at 67 kilometers per second. A galaxy 100 megaparsecs away recedes at 6,700 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 67,000 kilometers per second, more than 20% of the speed of light. And a galaxy at roughly 4,300 megaparsecs, 14 billion light-years away, recedes at the speed of light itself. Everything beyond that distance is, in the most literal physical sense, beyond our reach forever. And that horizon is shrinking. As the expansion accelerates, the distance at which recession velocity equals the speed of light decreases over time. The cosmic horizon is not a fixed boundary. It is a closing wall, moving inward, in terms of what we can ever influence or receive signals from, with every passing billion years. The Atacama Cosmology Telescope, operating in the Atacama Desert of Chile at an altitude of 5,190 meters, high enough that most of the water vapor in Earth's atmosphere sits below, has produced some of the sharpest measurements of the cosmic microwave background temperature and polarization ever obtained from the ground. Its data, combined with Planck, constrain the geometry of the universe to be flat to within a fraction of a percent, meaning the total energy density of the universe is equal to the critical density, the value at which space is neither positively curved like a sphere nor negatively curved like a saddle. This flatness is one of the most precisely established facts in all of cosmology, and it has a direct implication. The cosmological constant, or whatever dark energy actually is, makes up exactly the amount needed to bring the total energy budget of a spatially flat universe to closure. This near-perfect flatness is itself a clue. In the earliest moments after the Big Bang, during the epoch of cosmic inflation, the period of exponential expansion driven by a different scalar field, the inflaton, which ended approximately 10 to the power of negative 32 seconds after the origin of time, the geometry of space was driven toward flatness with extraordinary precision. The same mechanism that flattened space in the first instant of the universe's existence may be operating again today, on vastly longer timescales, through the agency of dark energy. Whether dark energy and the inflaton are related, whether the same class of physical field drove inflation at the beginning and drives acceleration at the present epoch, is an open and actively investigated question in theoretical cosmology. The James Webb Space Telescope, operational since 2022, has added its own layer of complication to the cosmological picture. Its observations of galaxies at redshifts above 10, looking back to a time when the universe was less than 500 million years old, have revealed a population of massive, well-formed galaxies that appear far too large and far too structured to have assembled in the time available under standard lambda CDM. Some of these galaxies contain stellar masses comparable to the Milky Way, fully formed within the first few hundred million years of cosmic history. The standard model of galaxy formation, which requires dark matter halos to assemble hierarchically over billions of years before galaxies can form within them, struggles to produce objects this massive this early. These are not definitively in conflict with lambda CDM. The statistical significance of individual outliers is limited, and systematic uncertainties in stellar mass estimates remain large. But the pattern is consistent, and it points toward either a revision in our understanding of early galaxy formation physics or a modification to the underlying cosmological framework itself. The universe at high redshift is not behaving exactly as the standard model predicts. The universe at low redshift is expanding faster than the standard model predicts and clustering less than it predicts. And the dominant energy component, the one that controls the ultimate fate of everything, is showing the first tentative signs of being something more complex, more dynamic, and more consequential than a fixed geometric constant. Every photon collected by every telescope now pointed at the sky is a data point in the most consequential scientific investigation in the history of civilization. The determination of what the universe is made of, how it will end, and whether the physics we have built over a century of extraordinary effort is complete, or merely the first chapter of something far stranger and far deeper than we have yet conceived. The answer is not in hand. The instruments are running. The universe is expanding, and the horizon is closing. Every atom in the human body was forged inside a star. That is not a metaphor. It is nuclear physics. The hydrogen in water molecules, in DNA, in the fluid of every living cell. Hydrogen formed in the first 3 minutes after the Big Bang, when the universe was hot enough and dense enough for protons to exist, but not yet cool enough for electrons to bind to them. The carbon, the nitrogen, the oxygen, the iron, Every element heavier than lithium was synthesized in the cores of stars through successive rounds of nuclear fusion, then scattered across interstellar space when those stars exhausted their fuel and either shed their outer layers as planetary nebulae or detonated as supernovae. The calcium in human bones arrived here via the death of stars that lived and died before the sun existed. The gold in the Earth's crust was forged in the collision of neutron stars, events so energetic they generate gravitational waves detectable across hundreds of millions of light years, and rain down onto the forming Earth during the period of heavy bombardment 4 billion years ago. We are, in the most literal and chemically precise sense, the universe examining itself. And what this particular arrangement of stellar material has discovered after 4 centuries of increasingly precise observation is deeply humbling. The matter that makes up everything we have ever seen, every planet, every star, every galaxy, every nebula, every cosmic ray, every photon ever detected by any instrument ever built, constitutes 5% of the total energy content of the universe. 5%. The remaining 95% is divided between 2 components whose fundamental nature remains unknown. Dark matter, which we detect only through its gravitational effects on luminous matter, and dark energy, which we detect only through its effect on the geometry of space-time itself. The universe is not primarily made of the stuff we understand. It is made, overwhelmingly, of mystery. This is not a failure of science. It is science working exactly as it should, pushing the boundary of the known outward until the boundary itself becomes the subject of investigation. The history of physics is a sequence of moments in which the framework that described all known phenomena turned out to be a limiting case of something deeper. Newtonian mechanics was not wrong. It was incomplete. It described the behavior of matter at speeds small compared to light and at gravitational fields weak compared to those near compact objects. General relativity subsumed it, extending its validity to regimes Newton could not have anticipated. Quantum mechanics revealed that the classical picture of particles with definite positions and momenta was itself an approximation, valid at scales large compared to the de Broglie wavelength, but fundamentally incorrect at atomic scales. Every expansion of the framework has preserved what worked before, while revealing that what worked before was not the whole story. The cosmological constant problem, the 120 order of magnitude discrepancy between the quantum field theory, prediction for vacuum energy, and the observed value of dark energy, is the largest such gap in the history of physics. It is a signal, not a nuisance. Signals of that magnitude do not arise from minor computational errors or small missing corrections. They arise from a fundamental mismatch between 2 frameworks, general relativity and quantum mechanics, that are each individually among the most precisely tested theories in science, but which have never been successfully unified into a single coherent description of nature. The unification of quantum mechanics and general relativity is the deepest unsolved problem in theoretical physics. It has been the central preoccupation of the field for nearly a century. String theory, the most extensively developed candidate for such a unification, predicts a vast landscape of possible vacuum states, each with a different value of the cosmological constant, ranging across an enormous range of values. In this framework, the question of why the cosmological constant has the value it does becomes a question of which vacuum state our universe occupies, and the anthropic argument that we observe this value because it is the only value compatible with the existence of observers acquires a concrete physical backdrop. But string theory has not produced a single confirmed experimental prediction that distinguishes it from existing frameworks. It remains mathematically rich and physically unconfirmed. Loop quantum gravity, the primary alternative approach, quantizes space-time itself, treating the geometry of space as a discrete structure at the Planck scale, where 1 Planck length equals approximately 1.6 times 10 to the power of negative 35 meters, a scale so small that a proton is to a Planck length as the observable universe is to a proton. Loop quantum gravity makes different predictions for the behavior of space-time at extreme densities and has implications for what happened at the Big Bang itself, potentially replacing the initial singularity with a quantum bounce, a prior contracting phase that rebounded into the expansion we observe. But loop quantum gravity also lacks confirmed observational tests. Both frameworks agree on one thing: general relativity, as currently formulated, cannot be the final description of spacetime. It breaks down at singularities, at the centers of black holes and at the Big Bang, where its equations produce infinities that signal the limits of the theory's validity, not physical infinities in nature. A complete theory of quantum gravity will modify general relativity in the extreme density regime, and may, almost certainly will, modify the cosmological constant problem in ways that current mathematics cannot yet express. Dark energy in this context is not just a cosmological curiosity, it is a window. Its measured value sits at the intersection of general relativity and quantum mechanics, too large to be explained by any known cancellation mechanism, too small to be the raw quantum vacuum energy. Whatever physics sets that value operates at a scale and in a regime that neither current framework can reach. Understanding dark energy may require, and may provide, the first observational purchase on quantum gravity itself. The irony is precise and worth holding. The largest structure in the universe, the accelerating expansion of spacetime across billions of light years, may be controlled by physics that operates at the smallest scale imaginable. The cosmological and the quantum, the largest and the smallest, the slowest and the fastest, connected by an equation whose form we do not yet know, whose solution we cannot yet write, but whose output we measure every night from mountain observatories and orbiting telescopes pointed at the edge of everything. The data from Euclid will be fully processed and published in stages through the late 2020s. DESI's 5-year dataset will reach completion around 2026, at which point the statistical precision on the dark energy equation of state will be sufficient to either confirm or decisively reject the hint of evolution seen in the first-year results. The Rubin Observatory's 10-year LSST survey will reach its full depth around 2035. The Roman Space Telescope will be operating by the late 2020s. Together, this generation of instruments will reduce the uncertainty on W to below 1%, a precision that will either vindicate the cosmological constant and force theorists to find new ways to explain its value, or confirm that dark energy evolves and open a new chapter in the physics of the universe so fundamental it will require rebuilding the theoretical framework from its foundations. Neither outcome is anticlimactic. A confirmed cosmological constant deepens the mystery of why quantum mechanics and gravity together conspire to produce a vacuum energy so precisely, improbably small. A confirmed evolving dark energy opens the physics of a new scalar field, with its own potential, its own couplings, its own history, that must be incorporated into a revised standard model of cosmology and, eventually, of fundamental physics. The universe does not simplify as we look more carefully. It deepens. 13.8 billion years ago, the universe was a state of almost perfect uniformity, a hot, dense plasma of particles and radiation, its density varying by only 1 part in 100,000 from place to place. Those infinitesimal fluctuations, imprinted by quantum processes during inflation, seeded everything that followed. The first density perturbations that gravity amplified over millions of years into the first gas clouds, the first stars that ignited in darkness after a cosmic gap called the Dark Ages, the first supernovae that seeded the interstellar medium with heavy elements, the first galaxies that assembled around dark matter halos, the first planetary systems where chemistry had access to, the full periodic table for the first time, and eventually, on at least one rocky planet orbiting a middle-aged star in the outer disk of an unremarkable spiral galaxy, the first arrangements of atoms complex enough to ask where they came from. That question, where did this come from? What is this made of? How does this work? Is the oldest question of the species and the animating force of all science. Dark energy is its current frontier. Not because dark energy is the only mystery remaining, but because it sits at the junction of everything we do not yet understand. The quantum vacuum, the geometry of spacetime, the ultimate fate of every structure in the universe, and the deep question of whether the laws of physics are what they appear to be, or merely the low-energy, large-scale shadow of something far more intricate. The expansion continues. Every second, the universe grows by a volume larger than the observable universe was when it was 1 billion years old. Every second, more galaxies cross the horizon and vanish. Every second, the The dark energy that fills each cubic meter of new space adds its infinitesimal contribution to a force that will, on timescales dwarfing the current age of the universe, determine whether all of this ends in cold and silent isolation or in a final, total dissolution of matter itself. We do not know which. We are taking the measurement. And in the act of measuring, in the patient, precise, cumulative work of building instruments and collecting photons and testing models against data, a 5% sliver of the universe has reached across 13 billion years of cosmic history to ask the universe what it is. That is not a small thing. That may be the most extraordinary thing that has ever happened.